In this video, we are going to talk about the differential geometry of curvilinear systems. This is the overview slide, which we'll spend a few brief minutes going over before we go over these two topics in more detail and more example. And this third topic, which I consider optional, we'll cover that in more detail as well. First, I will tell you the impact of the differential geometry of curvilinear systems. The first thing to know is the dot product, the line integral, surface integral, and volume integrals that we did in Chapter 2. They are just as they were presented in Chapter 2 because we were using the Jacobian when we went into our spherical and cylindrical coordinate. The next thing we will do is we will review the displacement vector, which we had discussed in our previous video, and we're going to review some points about it because that'll lead us into this figure here. And this figure here is important because when we come back here and look at integrating over a surface or volume, we integrate over an infinitesimal little piece of our domain is a small piece of our domain. And in this case, we're looking at a small volume that we would integrate over when we do a volume integral. And the thing you'll notice about this is it's not just the cube that we use to integrate when we use regular Cartesian coordinates. So this figure depicts a differential surface enclosing an infinitesimal volume in a curvilinear system, and then we'll look at how to translate then our rectangular system to a curved system. And what we will see is what we use to translate it is something called a scaling factor. And in our previous videos, when we did surface and volume integrals and we went into spherical or cylindrical coordinates, we multiplied them together and we called them the Jacobian. I consider this last topic somewhat optional. It's a good topic and it's not very long. However, you really can learn to do all the rest and move on to the other material in the book without really having seen this last topic here. Our first topic is the impact of differential geometry on curvilinear system, and it's no more than these two statements. So the dot product, line integral, surface integral, and volume integrals, as we did them in Chapter 2, they remain the same. It's the gradient, divergence, and curl that will change, and those will be covered in our next video. The next topic is a quick review of the displacement vector. If you recall, in curvilinear systems, such as this cylindrical coordinate system here, the basis vectors would change according to where you were in the space. And to get an expression for the ith basis vector, which we denoted q sub I with the hat. So the Cartesian coordinate basis, the standard basis is e sub I with the hat. Here we use q to designate a curvilinear basis. And we had the expression for our basis vector, our ith basis vector, associated with the coordinate q sub I, can be constructed by increasing q sub I and watching how the position vector changes and then normalizing. And you can see in this picture, if we increase phi a little bit, how it affects the change in position of our vector p will depend on our radius outwards that we're at. Because here, if we're at a small radius, our p, if we change phi by a little bit, our p will change a little bit. But out here, with a larger radius, you can see if we change phi by a little bit, p can change more. So again, the basis vector is going to change according to where you're located. In this case, if you're talking about changing phi, according to your radius. In our last video, we used this arc length formula to discuss how far p would change for a small change in phi. Coming back to our equation for the basis vector, we determined one in our previous video. Coming back to an equation for our basis vector, we had this equation that we looked at in our last video. So it tells us that the basis vector, we look at a change in r in the ith coordinate direction, and then we normalize. So here we have our dr. So our r is equal to our x1 coordinate, which is just x, q1, q2, q3 in cylindrical coordinates, q1 would be rho, q2 would be phi, and q3 would be z. And x of q1, q2, q3 is given by this equation here, rho cosine phi. Then we have our our x2, which is just y of q1, q2, q3 in the y direction, and then x3, which is z in the q1, q2, q3 in the z direction. We then take partial derivatives of r with respect to the ith coordinate, and that's over here. So if, for example, in cylindrical coordinates, we're looking to find the basis vector for phi, we would take the partial derivative of r with respect to phi. So over here, we would get minus rho sine phi. Here we'd get rho cosine phi, and here we would get 0. And then finally, we need to normalize. So we divide by the length of this vector here. So I have the length of the vector calculated as rho, so I divide this by rho, and that will give me my basis vector for phi. And this is the general equation for any system. It could apply to spherical or any other curvilinear system. And then finally, in our last video, we took another look at h of I, the scale factor that makes our curvilinear basis vectors unit length. It also has a physical interpretation. For a small change, delta q sub I of the coordinate qi, the position vector changes by a distance of the absolute value of delta q sub I times hi, which means our displacement vector then, if we move this delta qi, we need to multiply then our dr, multiply by partial derivative of dr with respect to our ith coordinate, which is equal to our small displacement times our h of I times qi. So that again means this h of I kind of tells us the distance that the position vector changes when we make a little change dqi. And that's going to have a direct impact when we integrate over a volume or an area. And we're going to look at this picture here, which depicts a differential surface enclosing an infinitesimal volume in a curvilinear system. And before we go into detail about this drawing, I just want to put this in perspective. Remember when you used to integrate and you would integrate over some range a and b of some function that's defined over a and b, and then the integration was defined or found to be, can be interpreted as a volume, an area under the curve. And what you would do is you would take a small piece of dx, that's this dx, you would evaluate it, at 2 points, and then what you would do a Riemann sum, so maybe you would sum at the midpoint or something, and then you would take that area, and then you would take the next small little dx, and you would keep going, and you'd get an area. When you did double integrals, you would have your domain down here. You'd go from a to b. This is a b. And in the y-axis, you might go from c to d, and you have some sort of domain over here. And then above, you've got some surface. But this this integral would be could be interpreted as a volume. And in the same way over here, you would take these little dx's. Here you would take a little square, dx dy. Maybe this little square here, you would evaluate the height of the function at one of the points in the square, and then you would get this little volume. You'd multiply this dx dy times the height, and you get a little volume. And then you would just move along, and you'd find your next dy dx, a little square, a height, find the volume. You just move along the whole domain, the domain that you're integrating over, and you'd get a volume. So you're integrating over the area to get a volume. Here you're integrating over the real axis to get an area. And sometimes we note this dx dy with the dA to emphasize we're integrating over an area. Finally, we have our triple integral. We're integrating with respect to a to b, c to d, e to f of dx dy dz. So we're taking little volumes, and above our volume, this dx dy dz, we have a surface. So it's like a hypersurface in 4 dimensions. But the idea is this f of x, y, z represents a value over a small volume piece of our domain. In much the same way over here, we had little area pieces. We divided up our domain into little areas. When we do the triple integral, we're dividing up our domain into little volumes, these infinitesimally little volumes that then we calculate our function over, sum it up, and we get our volume integral. And sometimes we write this dv to emphasize we're integrating over a volume. So that's what this cube is. It's this little infinitesimal cube we're integrating over, but now it's in curvilinear space. So the volume then is formed by choosing a starting point. So here we have Q1, Q2, Q3, that's our starting point. And then constructing 7 other vertices by moving away from this point with small changes of coordinate dq1, dq2, or dq3. So in the q1 direction, here's our q1 axis, we're going to move delta q1. And then to know the length of this, though, we need to multiply by our scaling factor, h1 of q1, q2, q3. Now we have another vertice. The other 7 vertices are here in green, 1, 2, 3, 4, 5, 6, 7. So let's just look here. When we move along the q2 axis, the length of this now is going to be delta q2 times our scaling factor for q2. So now we have a side along q1, a side along q2. So let's do q3, this one over here. So the length of this arc now, we're changing in the 3rd coordinate direction, delta q3, but we need to multiply to get this length of this arc. We need to multiply by our scaling factor, h3. Writing down what we just said, in the differential limit, the length of each edge along this warped cube are given by the appropriate delta qi times its scale factor. And the scale factor is evaluated at a set of coordinates that correspond to their initial value on the edge. And if the coordinate qi stays qi along the edge, it's set to qi. If the coordinate qi is equal to qi plus dqi along the edge, it's set to equal to qi plus dqi. If the coordinate qi goes away from qi to dqi on the edge, it's set equal to qi, just some conventions here. Now we can calculate our volume. We have this side here, our h1 times delta q1, our h2 times delta q2, and this length here is our h3 times delta q3. So this is our volume. And remember, our scaling factors are just constants, so we can pull those out. So we get delta q1, delta q2, delta q3, h1, h2, h3. Taking a look at this volume, this dv, this dq1, dq2, dq3, h1, h2, h3, in Cartesian, this would be dx, dq2 would be dy, dq3 would be dz, and h1 would be 1, h2 is 1, h3 is 1. So our normal dv would just be equal to dx, dy, dz. In spherical, we would have our first coordinate would be r, our second would be theta, our third would be phi, and then our h1 would be 1. h2, that's the scaling for phi, that would be r sine theta, and we worked that out in our previous video, and h3 for theta would be equal to r. So you can see that this is simply our dr d phi d theta times our Jacobian. To review what we looked at in this video, we looked at the impact of the differential geometry of a curvilinear system. We said the dot product, line integral, surface integral, and volume integrals, they remain the same as they're presented in chapter 2 because we used the Jacobian, and here we kind of interpreted or derived or said how we could come up with the Jacobian. The gradient, divergence, and curl, they do change, and they will be covered in our next video. We reviewed the displacement vector because it had this important impact of understanding that if we move in the direction of the ith coordinate, an amount delta qi, the amount we move our point changes by delta qi times our scaling factor h of I. And that is what helped us then get the volume of our infinitesimally small volume when we integrate over that. And that Here, when we move in the q1 direction by dq1, then the length of our change in our point P is going to be our scaling factor times delta q1. When we move in the q2 direction, we need to, when we calculate the length of the change in our position vector, that would be our delta q2 times our scaling factor. Similarly, when we move in the direction of our third coordinate, we need our delta q3 times our third scaling factor. And that was it for this video. Thank you for watching.